Section 3.2, page 155, number 15. The table shows the results of the survey in which 146 families, that's our total here, 146, were asked if they own a computer and if they will be taking the summer vacation this year. For Part A, we want to find the probability the randomly selected family is not taking a summer vacation. So we need to find summer vacation this year and no. And so for the no for the summer vacation is right down here, and that's going to be 45 out of the total 146. And so we're just going to make that a fraction and then divide it out. So that's just going to be 45 divided by the 146. And so when you divide that in your calculator, we're just going to go 3 decimal places, and that'll give us 0.308. And so that is the probability of a family not taking a summer vacation this year. Let's take a look at Part B. Part B asks us to find the probability that a randomly selected family owns a computer. So very similar to the last one. Family owns a computer, yes, 57 out of the total 146. So that's just going to be 57 out of 146. And so when you divide that out, and you can just relieve it as a reduced fraction depending on what they want, you end up with 0.390 with 3 decimals rounded correctly. For Part C, we're asked to find the probability that a randomly selected family is taking a summer vacation this year given that they own a computer. And that means that they are taking a summer vacation given, so summer vacation yes, given that they own a computer. So we're just looking at these people right here. So they're taking a summer vacation yes, given, you're only looking at the people that own a computer. So that's going to be 46 out of 57. And so we're going to divide that out, and in your computer when you divide that out for Part C you get 0.807. For Part C, we're asked to find the probability that a randomly selected family is taking a summer vacation this year and owns a computer. So the families that are taking a vacation, yes, and own a computer, yes, is 46, and they're just asking it out of the total 146. You only have to worry about changing the denominator when it says given, because you're only just looking at those ones. So it's going to be 46 out of 146. When we divide that out, you'll end up with 0.315. Part E asks us, are the events of owning a computer and taking a summer vacation this year independent or dependent? And the answer here is going to be dependent. The reason why is because of something similar to Part C. So that's going to be dependent because of the given. So if we're asking what's the probability of a family taking a summer vacation this year, the answer would be 101 out of 146. But if we asked what's the probability of a family taking a summer vacation given that they own a computer, that's only the 46 out of the 57. So they affect each other. That's why it is dependent. Section 3.2, page 157, number 22. 12 light bulbs are tested to see if they last as long as the manufacturer claims they do. 3 light bulbs fail the test. 2 light bulbs are selected at random without replacement. For Part A, we want to find the probability that both light bulbs fail the test. And so to calculate this probability, we're going to use our multiplication rules. So we want to have the probability the first one failed times the probability the second one failed, given that the first one failed. So the probability of a light bulb failing is 3 out of 12. So if you have 12 light bulbs and you took one of them out, now you've got 11 light bulbs left. Well, we're going to assume that we took out a failing one. That means we only have 2 failing light bulbs left. So probability of selecting a failing light bulb and then another failing light bulb is going to be 6, 3 times 2 is 6, over 132, which is 12 times 11. And so let's get that in the form of a decimal, which would be about 3 decimal places correctly would be 0.045. For Part B, we want to find the probability that both light bulbs pass the test. And so for this problem up here, we had an N of 12, which was the total number of light bulbs we had, and our fail was 3. Well, if we have 3 light bulbs that fail, then for the number of light bulbs that pass the test, because it's either failing or passing, is going to be 12 take away 3, which is going to be 9. So now we want to find the probability of 2 light bulbs that pass. So the probability of a pass times the probability of a pass, given that one is already passed. And so we're going to multiply the probability of pass, which is 9 out of 12, times the probability of another pass without putting the first pass back. So if you've got 1 light bulb that passed the test, and you took it out, you've only got 8 left. You had 12 light bulbs, you took it out, now you only have 11 left. So that gives us 72 out of 132, which is approximately, rounded 3 decimal places correctly, 0.545. For part C, we're asked to find the probability that at least 1 light bulb failed the test. So if at least one failed, that means both did not pass. We're going to use our complement rule for this. This is the complement that both passed. And so the complement rule means 1 minus. Well, the probability of both passing was from part B, 0.545. So the complement of that is 1 minus 0.545, which will give us, because this is approximation, an approximation of 0.455.